Hello, hello, hello. Check. Hello, hello everyone. Very good evening. Kindly confirm if audio video is clear. Okay, all good, all good. Thank you very much. So, hello everyone. Very good evening. Welcome back with the 13th lecture of discrete mathematics, and we are discussing set theory and algebra. What did we discuss in the last class? So, in the last class, we have understood the concept that how do we identify the order of an element of the group. So, what actually is the order of an element of the group? If A is any element and E is the identity element of the set, then the order of element A will be nothing but a least positive integer n such that A raised power n results in the identity element of the set. So what do I mean by this A raised power n? So this is the binary operation. It's not power of A, it's actually the binary operation performed on A n times. So that should be equals to identity element. So the least positive integer n such that A raised power n results in the identity element is called order of element, order of that particular element of the group. We have also understood the concept of subgroup. So if we have a group G comma asterisk, and if H is any subset of G such that H with respect to same binary operation asterisk is a group, then H with respect to asterisk is a subgroup of G. Now, very important property which we discussed in the last class is that order of subgroup, that is order of H, divides order of G. Order of subgroup will always divide the order of the group. So that's what we have discussed in the last class. Today, we are going to understand the concept of cyclic group, that when do we say that a group is a cyclic group, and apart from that we will try to understand the properties related to cyclic group, and we will learn some important properties related to general group. So these properties are very important because in current scenario MSQs can be asked, and in MSQs 2 or 3 of those properties can be given, and then they may ask that which of the following are true among this statement. So these are very important in the current scenario. Okay, so let's begin and try to understand the concept of a cyclic group. So very simple definition. So what actually is a cyclic group? If all the elements of the set of the group can be generated by some of the elements of that set, then that particular group will be called a cyclic group. So please try to understand what, let G comma asterisk be a group. So G is your set. If there exists an element A in the set G, if there exists an element A in the set G such that every element of set G such that every element of group G can be written in the form A raised to the power n. Again, A raised power n is nothing but A asterisk A asterisk A asterisk A n times A n times A. So, if there exists an element A in the group such that every element of the set can be written in the form A raised power n for some positive integer n, then your group will be called a cyclic group, and because we can generate every element of the set for the different powers of A, therefore A will be called generator of this cyclic group. So cyclic group, and element A is called generator of cyclic group G. Okay? Now let's try to understand with the help of example. So we know that, so we already know that 1 comma minus 1, 1 comma minus 1 is our group. 1 comma minus 1 is our group with respect to multiplication. So this time the operation will be multiplication. Check whether the above group is a cyclic group or not. Above group is cyclic group or not. So please try to understand. We'll try to see whether every element of the set can be generated by some of the elements of this set or not. So let's start with the first element. Let's start with the first element. If we start with 1, then some positive. So please remember, so this n has to be 1 or greater than 1 because we are saying for some positive integer n. For some positive integer n. So 1 raised power 1 will also be equals to 1. 1 raised power 2 will also be equals to 1. 1 raised power 3 will also be equals to 1. You need to understand that it can never generate minus 1. Cannot generate minus 1. Anyway, I'll give you an important information in a while, but that's fine. Now let's look for minus 1. Sir, minus 1 raised to the power 1 will be nothing but minus 1. Minus 1 raised to the power 2 is 1. That is the identity element. So please, okay, that's fine. I'll explain the other example, but that's fine. So this is 1. This 1 is equals to the identity. So do you realize that both the elements of this set can be generated using this element minus 1 for some power, some positive integer n, the power of minus 1. So all the elements can be generated. All elements of the set can be generated by minus 1. Therefore, group is a cyclic group and minus 1 is the generator. And minus 1 is the generator. That's first thing. Now, let's, okay. So we also know that, sir, for positive integer n, if a raised power n generates the identity element, then n is the order of that particular element. So you know that order of minus 1 is nothing but 2. Order of minus 1 is nothing but 2. So what is the order of this group? Sir, order of this group is also 2. Order of this group is also 2. Okay, so let's take another example. What, sir? 1 omega square is a group with respect to multiplication. Now, let's check whether it is a cyclic group or not. So, one thing is, sir, 1 raised power 1 will be 1. No matter how many times we raise the power of 1, it will remain 1. Now, you just need to understand one thing. Sir, if we have the identity element, no matter how many times we perform the operation of identity element with itself, it will remain identity element. So, e raised power 1 will be e raised power 2 will also be equals to e raised power 3 is also equals to e, and so on. So do you realize that identity element can never generate any other element of the set? Identity element can never generate any other element of the set. So one important property which you can write with respect to cyclic group is, so please let me write it here, you can note it down at the later point of time. What is it? So the first property is that identity element cannot be the generator identity element cannot be the generator of a set containing any other element except itself. So if identity element is the only element, then it's fine that identity element will generate itself. But if your set contains any other element apart from the identity element, then your identity element will not be able to generate any other element of the set apart from the identity element. Therefore, identity element can never be the generator of a cyclic group containing any other element apart from identity element. Now, sir, okay, one is the identity element, therefore one cannot be the generator of this group. Let's look for other elements. Let's look for other elements of the set. Sir, omega. Sir, omega raised power 1 will be omega. Omega raised power 2 will be omega square. Omega raised power 3 will be omega cube, which is basically 1 and it is the identity element. Okay, fine. If we increase the power any further, then we will keep repeating the same element. So do you realize that we have generated all elements? Sir, we can generate all element of the set using omega. So omega becomes the generator and this group becomes the cyclic group. So generated all elements. Therefore, group is a cyclic group. And omega is one of the generator. Okay. Now please try to understand. For power 3 of omega, we get the identity element. Therefore, order of omega is 3. Order of omega is 3. Sir, what is the order of this group? Sir, order of group is also 3. Order of this group is also 3. Now, let's check with respect to omega square. Sir, omega square raised to the power 1 will be omega square. Omega square raised to the power 2 will be omega raised to power 4, which is nothing but omega. Sir, omega square raised to power 3 will be omega raised to power 6, which will be 1 into 1, that is 1, which is the identity element. Again, all elements. Therefore, omega square is also the generator of the group. Omega square is also the generator of the group. Again, sir, what is the order of omega square? Sir, for what power of omega square we get the identity element? Sir, for power 3 of omega square we get the identity element. Therefore, order of omega square is also 3. Order of omega square is also 3. So, sir, in the previous case, order of the group is 2 and minus 1 is its generator. Order of its generator is also 2. In this case, order of the group is 3. Omega and omega square are the generators of this cyclic group. Order of omega and omega square is also same as the order of the group. So please, another property which we can write is that in a cyclic group G or Now cyclic group G, A, if element A belonging to G, if element A belonging to G is the generator of cyclic group G, generator of cyclic group G, then order of the element, order of generator is the same as the order of the cyclic group. Order of generator is same as order of cyclic. Order of generator is same as order of cyclic group. Okay, what else? Let's take another example and try to derive some more. Okay, sir. What? Let's of this. So we know 1, -1, iota and minus iota. 1, -1, iota and minus iota is the group with respect to multiplication. Is it also a cyclic group? Let's check. So 1 is the identity element, therefore it cannot be the generator. 1 equals to identity, therefore cannot be generator, cannot generate any other element except itself. Fine. So for another element, so what? The -1 raised to the power 1 is -1, -1 raised power 2 is 1, which is the identity element. Now if we increase the power any further, we will start repeating the element. Sir, what will happen? -1 raised power 3 will be -1, -1 raised power 4 will be 1. So the elements are repeated. So once you have obtained the identity element, if you were not able to generate all the elements of the set, then you will never be able to generate all the elements of that particular set for any power of that particular element, because once you have obtained the identity element, if you increase the power any further, you will start repeating the elements which you have already generated. You will start repeating the elements you have already generated. So please try to understand from here. What do we know? Order of -1 is equals to 2, which is not the same as the order of group. So what is the order of group? So order of group is 4. Order of group is 4. So not the generator. So okay, these two elements 1 and -1 are not the generator of this group. Let's look for remaining elements. Okay, sir. Sir, iota raised power 1 will be iota. Iota raised power 2 will be -1. Iota raised power 3 will be minus iota. And iota raised power 4 will be 1. All elements. Therefore, group is the cyclic group, and iota is one of the generator. Now you can actually see what, sir, because iota is the generator, therefore order of iota will be same as the order of group. Order of iota be same as the order of group, that is. And let's look for minus iota. So minus iota raised power 1 will be minus iota. Minus iota raised power 2 will be plus of iota square, which is -1. Minus of iota raised power 3 will be minus of minus of iota cube. Iota cube is minus iota, therefore it will become plus iota. And minus of iota raised power 4 will be 1. So again, all elements. all elements. Therefore, minus iota is also generator. So we know that order of minus iota is also same as order of group, that is 4. Yeah. So we understand one thing. What? Sir, in a set, if there exists any element, in a set, in a group, if there exists any element whose order is same as the order of the group, then that particular element, then the group will be cyclic group, and the element whose order is the same as the order of the group will be called generator of the group. So next note which we can write down is, we are already done with this points. Write down the third point. A group, comma asterisk, is a cyclic group. A group G comma asterisk is a cyclic group if and only if there exists at least one element A belonging to set G such that order of A is equals to order of G. So if there exists at least one element in the set whose order is same as the order of the group, then it is guaranteed that the group will be cyclic group, and element A will be generator of that cyclic group. Now please, one more point which we understand is that, sir, let's assume, come on. Sir, if omega is the generator of the group, then order of omega will be exactly same as order of its inverse. So if order of omega is 3, that is same as the order of group, then omega will be generator. And we know inverse of omega will also have the same order as the order of omega. That means inverse of omega will also have the same order as the order of group. Therefore, inverse of omega will also be the generator of this cyclic group. So what can we say? If element A is the generator of the cyclic group G, then A inverse will also be the generator of that cyclic group G. That's another thing. What? If element A belonging to G is the generator of cyclic group asterisk, then A inverse will also be generator of these cyclic, will also be the generator of G asterisk. Okay. Now, okay, so what else? So we have reached up to this particular point. Now, just look at this. Sir, you have given even enough example. You have given enough example of the groups which are cyclic. Can you please give us an example of a group which is not cyclic? Please try to understand. Sir, 1, 3, 5, 7. 1, 3, 5, 7 is a group. Is a group with respect to multiplication modulo 8. Check whether the group is a cyclic group or not. Check whether the group the cyclic or okay, let's check for different power. Sir, one is the identity, therefore cannot be the generator. What else? So 3. 3 raised power 1 will be 1. 3 raised power 1 will be 3. 3 raised power 2 will be what? So 3 2s are 9. 9 divided by 8, remainder 1. So this is the identity element. Come on. So once you have obtained the identity element, if you increase the power any further, you will start repeating the same element. So you can actually see that from here, order of 3 is equals to 2, which is not the same as order of group. So what is the order of group? So order of group is 4. There are 4 elements in the set. So there is 3. Order of 3 is not same as order of the group. Therefore, it cannot generate all the elements. We can actually see. So 3 raised power 3 will be what? So it will be nothing but 3 square with 3. So it will again be 3 raised power 4 will be nothing but 1, which is the identity element. So you will eventually understand that repeat rate. If you increase the power any further, element will start repeating the elements which it has already generated. Okay, sir. Oh, what, sir? 5. Sir, 5 raised to the power 1 will be 5. 5 raised power 2 will be 5 5s are 25 divided by 8. Remainder 1 is the identity element. Order of 5 is also 2, which is not same as the order of generator. Now 7 raised power 1 is 7. 7 raised power 2 will be 7 7 are 49 divided by 8. Remainder 1, which is the identity element. So order of 7 is also 2, which is not same as order of the group. So do you realize that no, in this particular group, no element is having its order same as the order of the group. Therefore, it is not a cyclic group. Therefore, it is not a cyclic group. Yeah. So, okay. So we can eventually write down here. No element. So no element of the group having its order same as the order of the group. Therefore, cannot be a cyclic. Because if the order of the element is not same as the order of the group, it will not be able to generate all the elements of the set. So it's simple. Now, let's take one more example and check what happens in that case. So, what do we know? 0, 1, 2, 3, 4 is a group. So, the set of all elements from 0 to n minus 1 will form a group with respect to addition modulo n. So, up to 5 minus 1 is a group with respect to addition modulo 5. What do we know? 0 is the identity element. Therefore, cannot be a group. Oh, sorry, cannot be the generator. Let's look at this. So, 1 raised power 1 will be 1. 1 raised power 2 will be 1 plus 1 divided by 5, remainder 2. 1 cube will be 1 square, addition modulo 5 with 1, that will be 2 plus 1, 3 divided by 5, remainder 3. 1 raised power 4 will be 4 1 raised power 5. We have already calculated the orders in the previous class, so don't worry that how am I getting these orders. So 1 raised power 5 will be 0, which is the identity element. So do you realize all elements? Sir, why? Because addition. Operation is addition modulo 5. Don't think that, sir, 1 square, 1 cube will always be 1. No. We are checking with respect to binary operation addition modulo 5. So what are we doing? 1 square will be nothing but 1 square will be nothing but 1 addition modulo 5 with 1. The result will be 1 plus 1 divided by 5 remainder. So remainder will be 2. That's what I'm doing. Don't get confused. Okay. Now, so all elements, therefore, 1 is the generator. Okay, now we have just seen that if 1 is the generator, inverse of 1 will also be the generator. If 1 is the generator, inverse of 1 will also be the generator. So what is inverse of 1? Sir, in a group with respect to addition modulo n, if x is the generator, n minus x will also be the generator. So if 1 is the generator, 5 minus 1 will also be the generator. So inverse of 1 will be 4. Therefore, 4 is also a generator. I'm not writing all the powers, but if you have any doubt, you can check that 4 raised power 1, 4 raised power 2, 4 raised power 3, 4 raised power 4 and 4 raised power 5 will be able to generate all the elements. Sir, for what power of 1 we are getting the identity elements? Sir, for power 5. So order of 1 is 5, which is same as the order of group. How many elements in the set? Sir, 5 elements. Therefore, order of group is 5. Order of group is 5. So we are done with 1 and 4. The next element is 2. So 2 raised power 1 will be 2. Obviously 2 raised power 2 will be 2 plus 2, 4 divided by 5. Remainder will be 4. So 2 cube will be 4. 2 square addition modulo 5 with 2. So 4 plus 2, 6. 6 divided by 5. Remainder is 1. So 2 raised power 4 will be 1 plus 2. 3 divided by 5. Remainder is 3. 2 raised power 5 is 3 plus 2, 5 divided by 5, remainder is 0, that is the identity element. Again, all elements, therefore, 2 is also a generator. 2 is also a generator. What is inverse of 2? Sir, if 2 is, what is the inverse of 2? So, n minus 2, that is 5 minus 2 will also be the inverse. So, inverse of 2 will be 5 minus 2, that is 3. Therefore, 3 is also a generator. Is also a generator. Okay, so sir, in this case, this will also be a cyclic group, and the generators of the cyclic group will be 1, 2, 3, 4. Let's go quickly and check. Sir, in this particular case, the only generator is -1. In this particular case, the generators are omega and omega square. In this particular case, -1 is not the generator, 1 is not the generator, but iota and minus iota are the generator. In this specific case, none of the element is the generator, therefore the group is not a cyclic group. In this particular case, except the identity element, all other elements are the generator of the cyclic group. Now the question arises that, sir, how do we check that how many, if the group is a cyclic group, how many generators will exist for that particular cyclic group? Okay, so that's the next note which we are going to write. So please, I hope it's clear to everybody that identity element will not be able to generate any other element except itself. Therefore, it cannot be generator of a group containing any other element except itself. Now, apart from that, the only element of the set that can be the generator of the group is the element whose order is exactly same as the order of the group. So, if there is no element whose order is same as the order of the group, then the group will not be a cyclic group. If there is any element whose order is same as the order of the group, then the group is guaranteed to be a cyclic group, and that particular element will be the generator of the cyclic group. Clear? Now, apart from that, the order of element is same as order of its inverse. Therefore, if a particular element is a generator, that means the order of that element is same as the order of the group. Therefore, the inverse of that element will also have the order which is same as the order of the group. Therefore, if element A is the generator of the group, then its inverse, A inverse, will also be the generator of the same cyclic group. Okay, now how many generators will be there? how many generators will be there? So next note, next property 5. What can we say? Let G comma asterisk is a cyclic group. So first of all, it should be cyclic, otherwise there is no point. Is a cyclic group of order n. G comma asterisk, the cyclic group of order n with element A belonging to G, with element A belonging to G as one of its generator. One of its generator. Then A raised power m will also be the generator of cyclic group. A raised power m will also be the generator of cyclic group G comma asterisk if G comma n will also be the generator of cyclic group G comma asterisk if m is less than n and co-prime to n. M is less than n and co-prime to n. So that is, if m is less than n, co-prime to n means that is if GCD of m and n is equals to 1. If GCD of m and n equals to 1. So that's a very important thing. Let's try to understand. Let's in this particular case, let's check. Sir, if 1 is the generator of this group, so what is the order of the group? Sir, 5 is the order of the group. Sir, what are the elements which are less than 5 and co-prime to 5? Sir, the elements which are less than 5 and co-prime to 5 are 1, 2, 3, 4. So if 1 is the generator, then 1 raised power 1, that is 1 will be the generator. 1 raised power 2, that is 2 will also be the generator. 1 raised power 3, that is 3 will also be the generator. 1 raised power 4, that is 4 will also be the generator. We already know that 1, 2, 3, 4 are the generators of this cyclic group. Similarly, this is not a cyclic group. We will not talk about. First of all, to calculate that how many generators are there, first of all, it must be a cyclic group. If it is not a cyclic group, there will be no generator at all. So that's a different thing. But if at all it is a cyclic group, then how many generators will be there? Sir, if G comma S is a cyclic group of order n, then element A belonging to G is one of the generator. Then A raised power m will also be the generator as long as m is co-prime to n and m is less than n. Anyway, so basically we are trying to say, just extend it, that is in our cyclic group, G comma asterisk of order n, in our cyclic group comma asterisk of order n, number of generators will be same as the number of numbers will be equals to number of numbers that are less than n, or number of positive, rather say, number of positive integers which are less than n positive, because obviously 0 will not have GCD equals to 1, which are less than n and O prime to n. So number of, how many generators will be there? Number of generators will be same as number of positive integers, which are less than n and co prime to n. Sir, again, number of positive integers which are less than n and co prime to n can be given by number of positive integers which are less than n and co prime to n can be given by, recall your 7th class mathematics formula, Euler's torsion function can be given by Euler's torsion function phi, Euler's torsion function phi n. Sir, how do we calculate phi n? What is the value of phi n? Sir, value of phi n is nothing but n into 1 minus 1 upon P1 to 1 minus 1 upon 1 minus 1 upon and so on, where P1, P2, P3, etc. are what? These are the prime factors of n. Are prime factors of n. Please, now let's try to understand this. We have already seen. So let's take a question. Find the number of generators in a cyclic group. Find the number of generators in a cyclic group of order equals to 4. Find the number of generators in a cyclic group of order equals to 4. So please try to understand what is n in this case. Sir, n in this case is 4. How can we write n? Sir, we can write how can we write 4? Sir, we can write 4 as 2 raised to power 2. Therefore, 2 is the only prime factor. 2 is the only prime factor of 4. Therefore, what will be the value of phi 4? Value of phi 4 will be nothing but n into 1 minus 1 upon first prime factor. First prime factor is 2. Do you have any other prime factor? No, sir. It will come out as 4 into 1 minus 1 by 2 is 1 by 2. Cancel out will be 2. You can actually see, we have seen some groups of order 4. Sir, this is your group. This is your cyclic group of order 4. So cyclic group of order 4. If somebody asks you that what will be the generator, then you will have to check explicitly. If somebody asks you that what are the generators of this cyclic group G, then you will have to check explicitly that what all elements can generate all the elements of this particular set. But if somebody is only interested in knowing that how many generators will be there for this cyclic group, how many generators will be there for this cyclic group, then you don't need to go and calculate explicitly. Based on the order of that particular group, you will be able to determine that how many generators will be there in that particular cyclic group. So but it is important that it has to be a cyclic group. So it is a cyclic group, therefore number of generators, if at all the group of order 4, if at all the group of order 4 is a cyclic group, then there will be 2 generators. But what if the group of order 4 is is not a cyclic group. If it is not a cyclic group, obviously there will be zero generators. Obviously there will be zero generators. Therefore, please focus. If G asterisk is a cyclic group, first of all, you must know that it is a cyclic group. If it is a cyclic group, then how do you calculate the number of generators of that particular cyclic group if the order of that group is n? So, the number of generators of the cyclic group can be given by Euler-Quotient function pi n. How do we calculate pi n? So, if n is an integer such that p1, p2, p3 up to pk are its prime factors, then pi n will be nothing but n into 1 minus 1 upon p1 into 1 minus 1 upon p2 into 1 minus 1 upon p3 up to 1 upon 1 minus pk. So how many terms will be there? It depends on the fact that how many prime factors are there of your number n. Okay, so just in this particular case, it is the simple case. Now let's try to understand what if the value of n grows larger. So if G the cyclic group of order equals to 50 is a cyclic group of order equals to 50, then find the number of generators of cyclic group G. So there are two ways. First of all, you can identify, you can explicitly go and check that how many numbers are there, how many positive integers are there which are less than 50 and co-prime to 50. So if you go and start writing them, then also you will get your answer. So the number of positive integers less than 50 and co-prime to 50 are what are they? So 1 is co-prime to 50, 2 is not co-prime to 50, 3 is co-prime to 50, 4 is not co-prime to 50, 5 is not co-prime to 50, 6 is not co-prime to 50, 7 is co-prime to 50, 8 is not co-prime to 50, 9 is co-prime to 50, 10 is not co-prime to 50, 11 is co-prime to 50, 12 is 12, 1, 2. 12 is not co-prime to 50, 13 is co-prime to 50, 14 is co-prime to 50, 14, 15 is not co-prime to 50, 16 is not co-prime to 50, 17 is co-prime to 50, 18 is not co-prime to 50, 19 is co-prime to 50, 20 is not co-prime to 50, 21 is co-prime to 50, 22 is not co-prime to 50, 23 is co-prime to 50, not odd, is 23 is co-prime to 50, 24 is not co-prime to 50, 25 is not co-prime to 50, 26 is not co-prime to 50, 27 is co-prime to 50, 28 is not co-prime to 50, 9 is co-prime to 50, 30 is not co-prime to 50, 31 is co-prime to 50, 32 is not co-prime to 50, 33 is co-prime to 50, 34 is not co-prime to 50, 35 is co-prime to 50, 35 is not co-prime to 50, 36 is not co-prime to 50, 37 is co-prime to 50, 38 is not co-prime to 50, 39 is not co-prime to 50, 40 is not co-prime to 50, 41 is yes co-prime to 50, 42 is not co-prime to 43 is co-prime to 50, 4 is not co-prime to 50, 45 is not co-prime, 46 is 40, 46 is not co-prime to 50, 47 is co-prime to 50, 48 is not co-prime to 50, 49 is co-prime to 50. So how many are they? How many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Sir, 20 such numbers. So either you can go and list all those numbers which are less than 50 and co-prime to 50 and count them and can say that there will be 20 generators of this cyclic group, or otherwise you can use the Euler's torsion function. So what is the value of n? N is actually 50. So how can I write 50? So 50 can be written as 2 into 5 square. So this is your first prime factor. and 5 is your second prime factor. Therefore, what will be 550? Sir, 550 will be nothing. 550 will be nothing but 50 into 1 minus 1 by 2 to 1 minus 1 by, okay sir, what do we get? Sir, we get 50 to 1 by 2 to 4 by 5. 5 2s are 10, 5 and 5 4s are 20. So you will get the same value, that there are 20 such integers, positive integers, which are less than 50 and co-prime to 50. So either go and count them or use this Euler's torsion function. You will get the same result, that the number of generators of cyclic group of order n will be number of positive integers which are less than n and co-prime to n, or it can be given by Euler's torsion function phi n. Both of them are same. So anyway, we are done with all the basic concepts related to concept of cyclic group. Now let me write down some important properties of the group. Sir, what are they? Some important. So these are not only with respect to cyclic group, these are the general properties. So please try to understand. Try to understand. What? The first property is every cyclic group is abelian. I'm not going to write each and I'm not going to define the proof of everything, but please remember that every cyclic group is abelian. I can give you one intuition. Let's assume if it is a cyclic group, if you have P cross Q, right? So the idea is that, sir, if it is a cyclic group and let's assume A is the generator, then we can write P in the form of A raised power R and we can write Q in the form of some positive integer A raised power S. So basically we are writing A raised power R binary operation with A raised power S. So basically it's nothing but A raised power R plus S, and it can be written as A raised power S plus R. So it can be written as A raised power S binary operation with A raised power R. A raised power S is basically nothing but Q, and A raised power R is nothing but P. That means P by Q will be equals to Q by R. Therefore, every cyclic group will be abelian. And I'm not going in too much detail, but that's fine. Right? So every cyclic group is abelian. Another is every group of prime order. Come on, I'll give you the intuition. Every group of prime order. That means if the number of elements in that particular group are equal to a prime number, so every group of prime order is a cyclic group. Why, sir? Why? Sir, yesterday only we said that the order of element of the group will divide the order of the group. Order of an element of the group will divide the order of the group. Now let's assume that order of group G a prime number. So the idea is if element A belongs to G, if element A belongs to G, then order of A divides this prime number P. Now there are only two numbers. Which can divide a prime number, that is 1 or P. So 1 with respect to identity. Now except identity element whose order is A, every other element will have order as P. Every other element will have, we have the example, order equals to P. Every other element will have the order equals to P. Now, if the order of an element is same as the order of the group, it will be the generator. If order of element is same as order of the group, that is P, then it will be the generator. So, if at all your group is of prime order, then accept the identity element. Every element will have the order same as the order of the group, and every element except the identity element will be the generator. Sir, do we have an example? Yes. Sir, come back to this particular point. So what is the order of this group? Sir, order of group is 5. So 5 is a prime number. Now, the idea is if 5 is a prime number, then every element except the identity element will divide the order of this group. That means except the identity element, every other element should have its order equals to 5. Should have its order equals to 5. You can see order of 1 equals to 5. Now, if order of 1 equals to 5, order of its inverse will also be equals to 5. That is, order of 4 will also be 5. Order of 2 is, you can check, sir, order of 2 is 5. Order of 2 is also 5. Now, inverse of 2 is 3. Therefore, order of 3 will also be 5. So, order of 1 is 5, order of 4 is 5, order of 2 is 5, order of 3 is 5. Order of identity element is 1. Order of identity element is 1. So, if the order of the group is a prime order or prime number, then every element except the identity element will have its order equals to the order of the group. That means every element except the identity element will be the generator of the group, and then obviously if the generator exists, then the group will be a cyclic group. Therefore, what can we say? That every group of prime order is a cyclic group. Every group of prime order is a cyclic group. Okay. Now, sir, we know every cyclic group is abelian. Now, every group of prime order is cyclic, so it is guaranteed to be abelian also. So, the third note which you can write down is every group of prime order is abelian. Every group of prime order is abelian. Fourth point, every group of order less than equals to 3 is cyclic. Okay, sir. Now, every group of order 4 except plane 4 group is a cyclic. Sir, what do we mean by plane 4 group? So, what do we mean by plane 4 group? Properties of plane 4 group. What is the property of plane 4 group? Property of plane 4 group is order of group equals to 4. Second property, every element is inverse of itself. Third property, binary operation on any two non-identity element. Binary operation on any two non-identity element must result in third. So obviously, if the order of group is 4, then that means the identity. So there will be one identity element. Apart from that, there will be exactly 3 non-identity. So if it is a group, then there will be in total 4 elements. One of them will be identity element. Remaining 3 will be non-identity element. So except the identity element, if you perform the binary operation on any two non-identity element, the result should be the third non-identity element. So element must result in third non-identity element. Okay, so do we have an example? Yes, we have examples. So where exactly? Now go back. The only example which you have seen of order 4, which is not a group. Let's look at this. Sir, order 1 is the identity element, therefore inverse of 1 will be 1. Now 3, binary operation with 3 produces the identity element, therefore inverse of 3 will be 3. 5 binary operation with 5 produces the identity element, therefore inverse of 5 will be 5. 7 binary operation with 7 produces the identity element, therefore inverse of 7 will be 7. So we know that inverse of every element, order of the group is 4, inverse of every element is the inverse of element is the element itself. Now sir, non-identity, sir, 3 5s are 15, divide by 8, remainder 7. So binary operation of 3 and 5 will produce 7, binary operation on 3 and 7 will produce 5, binary operation on 5 and 7 will produce 3. So if this property is satisfied, then group of order 4 will not be a cyclic group, and we know it is not a cyclic group. And we know it is not a cyclic group. Clear? Anyway, it's very obvious that if every element is inverse of itself, then identity will element will have order equals to 1, and if every element is inverse of itself, then every other element will have order equals to 2, and order of the group is 4. So no element of the set will have order same as the order of the group. Therefore, it cannot be a cyclic group. Therefore, it cannot be a cyclic group. Okay, fast. So this is the 𝐂𝐴4 group. Please remember, 𝐂𝐴4 group is not a cyclic group, but it is an abelian group. 𝐂𝐴4 group is not a cyclic group, but is an abelian group. So, having said that, that is not a cyclic group but abelian group, if we know that every group of order 4 except the 𝐂𝐴4 group is a cyclic group, so we can say one thing. What, sir? Every group of order 5, sir, up to 4, up to element 4, every other group except the 𝐂𝐴4 group is cyclic, and 5 is a prime number. So every group of prime number, every group of order 5 is guaranteed to be cyclic. So we know up to order 5, the only group which is not cyclic is 𝐂𝐴4 group of order 4. So every group of order less than equals to 5 except 𝐂𝐴4 group of order equals to 4 is a cyclic, of order equals to 4 is cyclic, and we know that every cyclic group is abelian. The only group of order 4 which is not cyclic is 𝐂𝐴4, but it is abelian. So can we say that every group of order less than equals to 5 is abelian? We can say every group of order less than equals to 5 is abelian. Seventh point which we can write down is every group of order less than equals to 5 is abelian. Okay, now last point. Now if you have a cyclic group, then its subgroup will also be a cyclic group. So subgroup of a cyclic group is also a cyclic group subgroup of a cyclic group is also a cyclic group, but generator of the cyclic subgroup, but generator of the cyclic subgroup need not be same as generator of main group. Main means from which it is or obtained. So, sir, do we have an example? Yes, we have example of everything. What? Sir. So what do we know? 1 minus 1 iota minus iota is a cyclic group of order 4. It is a cyclic group of order 4. We know that 1 comma minus 1. We know 1 comma minus 1 is a subgroup. 1 comma minus 1 is a subgroup of this group. So this is cyclic, and 1 comma minus 1 is a subgroup of this. So that will also be cyclic. But In the cyclic subgroup 1 comma minus 1, the generator is minus 1, whereas in this particular case the generators are iota and minus iota. So generator of a cyclic group is guaranteed to be cyclic. Generator of a cyclic group is guaranteed to be cyclic. But the generator of the cyclic subgroup need not be same as the generator of the main group. Please try to understand. I am only saying that generator of a cyclic group is guaranteed to be cyclic, but it does not mean that if the group is not a cyclic group, then its subgroup cannot be cyclic. So obviously we know that if the group is cyclic, then its subgroup is guaranteed to be cyclic. But if the group is not a cyclic group, then its subgroup may or may not be cyclic. We are not giving any comment about that. Clear? So we are done with all the concepts of cyclic group. So we have understood that what do we mean by cyclic group. If there exists any element n, if there exists any element a such that every other element of the group can be written in the form a raised power n for some positive integer n, then the group will be called a cyclic group and element a will be called generator of the cyclic group. Some important property: identity element cannot be the generator of a cyclic group containing any other element except itself. Order of the generator will be same as the order of the group. Now, if element A is the generator, A inverse will also be the generator. If there exists at least one element in the group whose order is same as the order of the group, then the group is guaranteed to be cyclic. If there is no element whose order is same as the order of the group, then it cannot be cyclic, and so on. Now, apart from that, we have seen some important properties. Then how many number of cyclic groups will be there? If G is a cyclic group of order n, then the number of generators of a cyclic group G will be same as the number of numbers which are less than number of positive integers which are less than n and co-prime to n. It can be given by Euler's torsion function by n. Apart from that, we have seen some important properties based on which some MSQ questions can be framed. So please follow all these concepts properly. In the next class, we'll have two different sessions for the previous year questions of set theory and algebra. So I have discussed sets and I have discussed the concept of sets and relation. I have discussed the concept of functions, and I have discussed the concepts of group theory. So I have completed all the concepts of set theory and algebra. In the next two sessions, I will discuss the good quality questions from GATE previous year paper. Okay, so that will be all that is upcoming in the future. Till then, take care, keep learning, have a nice time. Bye bye.